Today we're going to begin Chapter 5, and Chapter 5 deals with logs and LNs and natural logs and all the different exponential functions, and we'll be running through derivatives and properties of logs and integrals of logs and all of those things in this chapter. So to start out with today, we're going to define the natural log, and the natural log is a log with a base e. Most of us have seen it written as the ln of x or whatever number we're talking about. Natural log's abbreviation is ln. You'll find that on your calculator. There's properties of the natural log function. The properties that we want to make sure that we know is that the domain runs from 0 to infinity, and the range is from negative infinity to infinity. The second thing we want to know is that the function is continuous, and it's increasing, and it's one-to-one. One-to-one, what does that mean? Maybe you don't know. This function, this is what it does look like. Okay, this is a really fast sketch of it. One-to-one means that if you do a horizontal line test, that the horizontal lines will only pass through the graph in exactly one spot. Very similar to that vertical line test, but a vertical line test just tells me whether or not it's a function. A horizontal line test tells me whether or not it's one-to-one. And the last thing that we're going to know about the function is that it's concave down. There are properties of logs that you need to know. At some point in time, you've probably talked about these before. This should be review. This first one, ln of 1 is 0. That's something that you absolutely must need to know. The second one, if you have the ln of two numbers or two things being multiplied together, you can actually separate them into two ln's. So it would be the ln plus, or ln A plus ln B. So the product of A and B actually turns into the sum of ln A plus this ln B. The next property talks about if you have something a to the n, so you have an exponent, you can actually bring the exponent out front to simplify it. And the last property is that the ln of a divided by b can be rewritten as the ln of a minus the ln of b. The first problem I want to go ahead and talk about says, use a graphing calculator to evaluate the logarithm by using the natural log key. So that's the first thing I'm going to do is I'm going to bring up my calculator and I'm going to find the log key on it. Right here is the natural log. So I'll type in the natural log and I'll go back to see what the number is, 8.3. 8.3. I'll close those parentheses and I'll hit enter. That gives me the decimal of 2.116. So I'll go back and write in that answer, 2.116. Part B asked me to use the integration capabilities to evaluate the integral. Please feel free to ask me about how to use your calculator and the integration capabilities. Some of your calculators will look similar to the one I'm going to bring up. But what we're going to do is we're going to put in the integral from 1 to 8.3 of 1 divided by t dt. And I'll do that on the calculator right now. So I'll type in my integral and I'll put in from 1 to 8.3, and then my function itself is 1 divided by x. We'll call it 1 divided by x, and I'll hit enter. Notice I get the exact same answer what I got before, so you can use integration to actually find the natural logs. So I'll go ahead and write down that this is the same answer. Alright, the next thing I want to go ahead and do with the logs is I want to go ahead and graph those. So what I want to start out with first is just what does the natural log look like. So what I'm going to do is actually create just a sketch of this picture. One of the things that I know is that if I put 1 in for x, I end up getting 0. So I'm going to go ahead and put that point definitely on this graph as 1, 0. What we know is that this graph gets closer and closer to the y-axis but never crosses it. And also we know that this function as it's going to the right is increasing continuously. This entire thing is concave down. What does this do? This plus 1 on the end, all it is going to do is shift that graph exactly 1 up. So instead of this point being at 1, 0, it's now going to be at 1, 1. Everything else stays exactly the same. This next one, the plus 1 on the inside actually shifts it 1 to the left. So instead of that point being at 1, 0, it's now at 0, 1, because if I put 0 in there, I would get the ordered pair. Put 0 in there, ln of 1 is 0. So I end up with the point 0, 0. So that means that my asymptote, actually this graph is going to get closer and closer to negative 1 without ever crossing it, and then increasing as it goes off to the right. The negative ln flips the graph over the x-axis. So it's still going to cross at 1, 0, but now it's going to be concave up instead, and always decreasing. The next type of problems we're going to look at are using the properties of logarithms, and we're going to approximate the indicated logs. So I'm given that the ln of 2 is 0.6931 and the ln of 3 is approximately 1.0986. How does that help me? Well, 3 times 2 is actually 6. So really this says the ln of 3 times 2. The property when you have two things that are multiplied together is that you can separate them by putting a log 3 plus the ln of 2. So I should have said ln. This is the natural log of 3 plus the natural log of 2. Then what I can do is go ahead and replace that as 1.0986 plus the ln of 2 is 0.6931. Those will add to give me approximately 1.7917. In the next example, I have to figure out, I only know things about 2 and 3, so I have to figure out some way of getting 81. Well, I know that 9 times 9 is 81, and so that means that 3 times 3 times 3 times 3, so 3 to the 4th power is 81. That means I can use the property that says bring that exponent out front, write ln of 3. I'll replace the ln of 3 with what it is equal to, 1.0986. And then I'll multiply those together to get my answer of 4.3944. We're going to continue to use the property of logs. This time we're just not going to be solving any, we're just going to write them in an expanded form. So this first problem actually says the natural log of 5, or x to the 5th, to the 1/2 power. So really what I have is of the natural log of x to the 5/2 power. So that means I really could finish this off by writing it as 5/2 ln of x because of the property that says I can bring that out front. I'll continue these next problems on the next video. Alright, continuing on with these problems here, what I have is another two things being multiplied together. So I have the ln of 3 plus the ln of e squared. So I'm actually going to use the second property and write this as ln 3 plus, bring this 2 out front, 2 ln e. Now one of the things that you may or may not know is that ln and e cancel each other out. They create a 1. So we are going to keep that tucked away in our minds so that when we see ln of e, we're going to say, well, that's just really 1. And so 1 times 2 is 2. The reason why it is 1 is because the ln, the natural log of e, has a base of e. The last example on this page uses the rule of division. So we'd say ln of 1 minus the ln of e. We know the ln of 1 is 0, and we know the ln of e is 1. So that means that my answer would just simply be negative 1. We have a new type of problem that we're going to work with, which says write the expression as a logarithm of a single quantity. So this time, instead of writing it expanded form, I'm going to go the other direction with my properties. So the first rule I'm going to do is with the exponents, and I'm going to pull those numbers out in front back up to be exponents. Then the next thing I want to do is go ahead and use the rule of multiplication. So these two are being added together, so it means that they are really a product. And then what we'll do is we'll put that divided by, because the subtraction sign uses the division rule, of z to the 4th. In this next problem here, I will first just work with everything inside the parentheses. So I'll go ahead and say this is the ln of x divided by x plus 1. And then what we would have is minus ln of x minus 1. Well, I could then use the division rule again and put those together. So this would be x over x plus 1 divided by x minus 1. So it'd be like multiplied by the reciprocal. So I'd have x over x plus 1 times x minus 1. If you wanted to, you could write that as x squared minus 1. And then the last rule I would use is bringing that 2 out front or up top with as the exponent. On the next problem here, we're talking about finding the limits. On this particular problem, if I plug in 6, I get ln of 0, and that doesn't exist. It says find the limit as x approaches 6 from the left. Well, you could graph this problem, but one of the other things we can always use is just test numbers. So something that's really, really close to 6 from the left would be 5.99999. So when you plug that in, you'd really be finding out what's the value of the ln of 0.0001. So let's go ahead and do that real quick. Find the ln of 0.0001. That gives me a negative 9. Well, let's see what happens if we get even closer. So this becomes even smaller. Notice what happens is I get even a more negative number. So what that means is that this limit is actually approaching negative infinity. On the second example, we always want to try plugging in the number first. So I get ln of 5 over the square root of 1. Well, that works out just fine. I can just say this is equal to the ln of 5. When I want to know what the ln of 5 is, I just type it in. ln 5 is 1.61. So I could say this is approximately 1.61. Alright, the last example I'm going to do is define the equation of a tangent line to the graph of the logarithmic function at the point 1, 0. Now I've even defined how to find the derivative, which we know that's what we need to be doing when we find the tangent line to the curve. So I'm going to go ahead and do that. The derivative of the ln of x is equal to 1 over x. Now if this is anything other than an x, so I'll give you an example. Let's say it says ln of x squared. We would write 1 over x squared times, we'd have to remember to take the derivative of this just like we do when we have a cosine or a sine or something along those lines. So we're going to go ahead and find this derivative first because that will tell me the slope of the tangent line of the curve. So I get 1 over x to the 3 halves. And then that would be multiplied by, we have to take the derivative of this part. So 3/2 x to the 1/2. I'm going to go ahead and rewrite this just a bit. So I get my 3 x to the 1/2 on top and all of this on the bottom. Now I'm really concerned about just at this point, so I'm going to plug in 1. So I end up with 3 times 1 over 2 times 1. So the slope of the tangent line to the curve is 3/2. So I'm just going ahead and quick write the equation of the line. Y minus 0 equals 3/2 times x minus 1. Now we could simplify that if we wanted to just be y equals 3/2 x minus 3/2.